Okay, this is number 29 in section 3.3. First derivative test. We're going to do the first derivative test on this function, x plus 2 to the 2/3 power. And while I'm thinking about this, I think maybe I'll talk a little bit about exponents, what that does to functions. So this is kind of obvious. It's kind of interesting. If you have, if I have a function x squared, it kind of goes like this. If I have a function x, it goes like this. If I have a function x to the 1/2 power, it goes like this. So you can kind of think of this, 45-degree angle line is x to the first. This is x to the first power. So anything an exponent greater than 1, the curve is going to go up. An exponent less than 1, the curve is going to go down like that. So that's an interesting, a useful thing to remember about, when I look at this function here to the 2/3 power. So I would expect that. I would expect to the 2/3 power to look something like this. So here is x to the first power, just a straight 45-degree angle line. X to the second power goes up. X to the 1/2 power goes like this. So x to the 2/3 should do something intermediate there. I would imagine it goes like this, okay? So just think about that, logically. It's going to go up, but probably at a decreasing angle as it goes. The plus 2, what does that mean? The plus 2 inside the parentheses means it's going to move the function 2 units to the left. Remember, it does the opposite of what you think. Plus 2 you would think would move to the right, but it actually moves it to the left. So this thing is going to look something like this, I'm guessing. X to the 2/3 power, or x plus 2 to the 2/3 power is going to look something like that. Just from, being logical about it. So we'll see. We'll see if that's what happens. Now what happens over here, is going to be something else again. My guess is it'll go like that, but, we'll see. We'll see what happens there, okay? So we're going to do the first derivative test on this and see, kind of what that does to the function and what that tells us about the function. So if this is f prime is going to be 2/3 x plus 2 to the negative 1/3 power. And then, of course, you do have the chain rule inside here, but in this case, the chain rule is just 1 for dx dx, so there's not really much to say there. Okay? So let me get rid of that. We'll just write it like this. We'll rewrite that, in this form, 2 in the numerator, and then 3 in the cube root of x plus 2 in the denominator. Sometimes that makes it a little bit easier to see, what's going on here. Okay? So are there any critical points here? Remember, critical points are where this is going to equal 0. So critical points any places where this equals 0? No. There's no way to make that numerator equal to 0. If you have a fraction, the only way to make it equal to 0 is to make the numerator equal to 0. The denominator, if you make that equal to 0, you're going to get, an undefined point. And that does happen, right? So critical points, this is undefined, the derivative is undefined if x equals negative 2, because then you're taking a square root of 0, or cube root of 0, which is 0. That's okay to do that, but that's in the denominator, so it makes the first derivative undefined. So there will be a critical point at x equals negative 2. So what we're going to do is we're going to make our graph, and at negative 2, we're going to say, hey, there's something weird going on at negative 2. Let's make that a critical point right here. I don't know how we want to denote that, maybe with an arrow or something. Okay. And we're going to evaluate the first derivative to the left of that critical point and to the right of the critical point and see what happens there. So all I'm going to do is I'm going to take f prime. I'm going to pick a number over here, maybe negative 3. Put that into this function and see what that does. If I put negative 3 in there, I get 2 over 3 times the cube root of negative 1. And remember, you can take cube roots. Odd roots of negative numbers are okay. So the cube root of negative 1 is just negative 1. So this thing this equals negative 2/3. Okay? So over here, in this interval to the left of our critical number, the first derivative is going to be negative. Okay? It's undefined right here, but to the left it's negative. And then we'll see, you know, what happens to the right here. Let's pick a number over there to the right of the critical number, and the easiest there is always going to be, we can put 0 in there. So if I make x 0, I've got the cube root of 2. That's kind of a hard thing to do. Let's make it -1. That makes it a little bit easier. If I make x -1, then this is going to be 2 over 3 times the cube root of -1 plus 2 will be 1. So that'll equal just positive 2/3. So over here to the right, the first derivative is going to be positive, which means the function is going up. So over here on the left, the function is coming down. Over there on the right, the function is going up. Right there at the critical point, the function or the derivative is undefined, so there's probably a kink or something going on there, right there at the critical point. And that's going to be our guess, is that there'll be a kink there. So let's find the value of the function at the critical point. So what's the value of f? So I want to know f at when x is equal to -2, and that's 0, right? It's the cube root, or 0 to the 2/3 power. And 0 to the 2/3 power is just going to be 0. So right here, you know, that's the value of the function at that point. At -2, it's going to be 0. So my guess is that, you know, just like we said when we were discussing the, you know, what this function looked like before, is that it's probably going to go something like this. You know, so this will be x to the 2/3 power, x plus 2 to the 2/3 power. And over here on this side, I'm guessing it's going to be symmetric, and it'll be, you know, look something like that. So my guess is that there'll be a kink right there at that critical point. And we could verify that with the graphing calculator. All right, so hopefully that helps.